it's dx1 dx2 all integrated from minus infinity to infinity.
I'm using x1 and x2 on the right hand side. The first two lines, x1 and x2. No. It's left column. x1 and x2.
Left column?
No. The
Oh.
first two equations.
Yeah. Okay. Right. Okay. So as I was saying, when you do the expectation value, you certainly can take this square out, and since everything is real, there's no problem with conjugation. Okay. So then, let's think about this. Well, we will have a factor of minus h bar squared over 2m that's common to everything. Right? That is just maybe a unit of the energy. And then you can say, well, you're going to have a sign minus, and this is going to see the sign minus x1 on the other, for the other one, right? Because you're sandwiching this operator in between two copies of this. And then, well, you will have terms like psi plus x2 squared, psi minus x1, d squared, dx1 squared, psi minus x1, right? Because when this plus x2 and the minus x1 sees this operator, only the minus x1 gets operated on, while the psi plus x2 can be taken over here. And we know that this is normalized, right? So if I take one of these integrals, the x2 integral, this just becomes 1. Right? So I have some terms like this. And you can say, well, for all the other ones, I'm going to get maybe the plus will see the dx2 operator, right? And then the minus will just see a copy of itself. And because of normalization, that goes to 1. So we have 4 copies of this. And what do I mean? Well, due to the symmetry of these two wave functions, you can certainly say that psi x1 d squared dx1 squared psi plus x1. When integrated from minus infinity to infinity, there's no difference between these two. Right? And also, if I change x1 to x2, there's no difference, right? So if I define this factor to be proportional to E, energy of maybe the energy of the kinetic energy of a single wave packet, then I know that I have 4E in the total product, right? And then we're going to have cross terms. And because of this minus sign, the cross terms all require a minus sign here, because a plus on this side only for the cross term only sees the minus on that side. So there are going to be also 4 cross terms. And you can write down the cross terms as psi minus x1, okay, psi plus x1, and then psi minus x2 d squared dx squared psi plus x2. Okay. So you will have variations of this. You can just permute plus minuses and x1 and x2. So again, you have 4 copies of something like this. And they are all equal. Okay. So remember, for the cross terms, what we really have is integral over dx1 and integral over dx2. Right? Certainly these things are separable. So let me define the integral. Let me define an integral, which is the overlap between the wave functions. Right? You have some integral like this. And then let me define an integral which is the cross term coming from this operator, the kinetic energy operator. Okay. You can already see that because of the overlap of the wave functions, and because of this indistinguishability, the requirement to put a minus sign here. You have cross terms. You have cross terms in the kinetic energy. And this is effectively the interaction. So maybe you can do this algebra, and I'll tell you that the expectation value for the two-particle Hamiltonian in the fermion case is given by, you have 4 coming from the 4 copies of each of this, and then it's the normalization factor n squared And then inside is simply E minus gamma I. Okay. You can do this calculation and you'll see that for two fermions, compared to the 2-3 particle case where you just add the energies, the two fermions have a higher energy due to the overlap and due to the, yeah.
Were you supposed to finish the second line? Were you trying to say something on the second line? What were you trying to fill out?
Yes,
How do you fill it out, the second line?
Okay, but
What were you trying to fill
I'm
out?
just trying to say this is psi x1, x2, and then you have this.
And then the third line should have 4 functions, right?
Right, you have 4 columns.
No. You have psi plus, psi minus, psi minus. Or you have psi plus squared. That's what you meant. Okay.
Yeah, I have psi plus squared. Yeah. Right. So this is just a tractable way because we know how to integrate Gaussian integral. Right? So if you do this, there's a tractable way to see mathematically what does the Pauli's exclusion principle tell you. It tells you that actually for two fermions, when their wave function overlap and you require that the total wave function respect the symmetry under particle exchange, then you'll have an effective interaction. And then you'll see that for the two bosons, the effective interaction is attractive, okay, at long range. All right, so I'll leave this as a homework problem for you guys. Okay. So then on Thursday, we can talk about, let's see. I have something we did not finish today, so maybe on Thursday I can talk to you about how do we treat the case where there's a weak interaction inside of both our Fermi system. And that is the mean field approximation. And then after that, we're going to use the equation we derived from there to analyze the case of a Cooper pair condensate, and then we'll study the Cooper pair box problem.